This is a second lecture for the second half of Chapter 2 for ODE. And in this lecture, I will develop the characteristic polynomial for planar systems and introduce the words eigenvalue and eigenvector. Quite a bit of this lecture I'm going to show here in the slides, the written lecture, and the reason for that, it's important to get this concept correctly, and so I just want to go over it with you. So what I'm going to do is derive a solution method for these systems. Now there are two approaches to doing this, and both of them are valid. The textbook and some other approaches spend time, in fact start with concepts from linear algebra and then bring them into this to the ODE, to the solution of these systems. There's another approach, and I'm going to follow the other approach. It requires only basic knowledge of matrices, and then we're going to borrow terms from linear algebra, and we don't have to do an in-depth discussion of linear algebra. It's not required or necessary. So we're going to start with the system and write it in matrix form. dy by dt equals ay, where a and y are vectors. Y is the solution vector, and the solutions are called x of t and y of t for now. And A is a 2 by 2 matrix of constant coefficients. So A is just A, B, C, D in matrix form. It's a 2 by 2 matrix. Now the goal will be to find solutions x of t and y of t. A lot of times we'll be drawing these phase portraits and not seeming to pay any attention to the solutions. And the reason for that is that the phase portraits make distinctive patterns. You can see a center, you can see a source or a saddle pattern. But the solutions can have very different shapes depending on the initial condition. So they aren't as informative, although they are important, and of course they're always available. So the first thing I'm going to do in looking for the solutions is, actually I am going to find closed form solutions for these problems. And I'm going to borrow the idea that was used for that second order differential equation of the harmonic oscillator that we went through in the first 6 chapters. And that is, we assume that there's a time dependence, and the time dependence looks like this, e to the lambda t. But the difference here is that instead of having one variable for the second order differential equation, we had one variable, y of t, that we were solving for. Here we have two. Of course they're first order, but there's still two of them, x of t and y of t. So we assume that both x of t and y of t have the same time dependence, and they differ only by some constant that we'll call v of x for the x. And we're going to call this one, that's the x, and vy, e to the lambda t for y. So that's typed here instead of in my horrible handwriting. Okay, here's x of t. It is some constant, which I'm going to call v of x, times e to the lambda t. Here's y of t. It has the same time dependence, e to the lambda t, but it's multiplied by a different constant, v sub y. Okay. The constants vx and vy are not determined right now, and they're really not restricted except that both cannot be 0. If they're both 0, of course, we have absolutely no solution. So again, we're using this idea of e to the lambda t. We're going to put it through the equations. Obviously we have uniqueness and existence satisfied, so when we come up with a solution, it is indeed the solution, and we don't have to worry about that. So we're kind of encouraged also by the success that this method had for the second order equations for the harmonic oscillator. So again, I'll write it here in case you have forgotten it. We're saying that x of t is some constant times e to the lambda t. Y of t is another constant times e to the lambda t. Okay, and we're going to write that solution vector in terms of those. So here's x of t, I write it like that, and I can obviously factor out the e to the lambda t. So that gives me e to the lambda t, and the two constants vx and vy are now sitting there as a vector. So I will call them the vector v, which has significance, and which is why I chose the notation vx and vy. So e to the lambda t comes out, and in the solution form you're left with a vector v made up of those constants. So let me erase the screen here, and here with my assumption on the form for the solutions for x and y, I now have a different form for that solution vector y. Okay, and the v is a non-zero vector because remember we said both vx and vy could not be zero. That was the only restriction on those two, on vx and vy. Now we want to put all this into the differential equation, so we'll need the derivative. So when we take the derivative of y, which is the derivative of these two, we end up with lambda vx e to the lambda t, lambda vy e to the lambda t. Obviously the lambda and e to the lambda t can be factored out, again leaving that vector v. So we have dy by dt equals lambda e to the lambda t times v. Okay, and these are vectors. We could have done that by differentiating right here because v is not time dependent, but working through the steps we get the same thing. So now here we have the first derivative, we have y, and now we're going to put that into our equation, which is dy by dt equals a times y. So here is that equation that I wrote on the previous page. I substituted for dy by dt, I get this, a multiplying y, so I'll have a times e to the lambda t times the vector v, these are vectors, and I can write it like this. So at this point, let me factor out. So I'd have e to the lambda t, okay, it's lambda times v in this case, and over here will be e to the lambda t times a v. Okay, lambda is a scalar, and it's multiplying v. So if I multiply lambda by the identity matrix, which I know you know what the identity matrix is, of course, then I would have a matrix here. I can rewrite this term as lambda times I times v. Okay, you see that? I have to erase the board now. Alright, so over here I go like this, e to the lambda t, lambda times the identity matrix times v, that's the same as v, okay? And over here I have e to the lambda t, a v. So I can combine this onto one side. I'll have e to the lambda t, and this will be, well, I'll combine it onto the other side, so it's traditionally written like that, e to the lambda times I. Because now I can subtract these two matrices. See, if I just have lambda as a scalar, I can't combine it with a, and I can't factor out v, but now I can factor out v, and this equals 0. Okay, e to the lambda t is never 0, so I can forget that, and so I'm left with this. This is a very important equation right here. This is the big equation for solving these matrices, these systems. So it's a coefficient matrix A minus lambda, which is our assumed time dependence, times the identity matrix, so that's one matrix there, times that V matrix of those coefficients equals 0. So now to find the solution of the differential equation with the assumptions that we made, we need to find values for lambda and for V, because we already have assumed their form. Remember, just kind of want to always keep that in mind. We said that x of t was some constant, vx times e to the lambda t, and y of t is some vy e to the lambda t. It's going to have it's going to be of this form. So I'm looking for values for lambda, and I'm looking for v, which would mean I'm trying to find these constants, vx and vy, and lambda. Now there's some mathematical reasoning that we're going to do here that's going to give us first values for lambda. After that we find the v, once we find values for this that exponent in our solutions. So what we're looking at, just to remember this, I'll put it up here. We've got, well, I'll never learn. A minus lambda I times V equals 0. So now we're just going to discuss this matrix, A minus lambda times the identity matrix. All right. Its determinant could be 0 or it could be non-zero, right? That covers all the cases. Let's say it's non-zero. If it is non-zero, then there would be an inverse, right? Just a plain old square matrix, it will have an inverse. I could multiply both sides of this equation by that inverse, and I would have the inverse times this matrix times V, and it would be the inverse times 0. Well, inverse times 0 still gives me a 0 on this side, and here I would get the identity matrix, since this matrix operations, I get the identity matrix times V, which is V, which means V equals 0. But V cannot be 0 by our assumptions. We said V can't be 0 or we have no solutions. So this violates the assumption that the vector V is 0. That means that A minus lambda V must be non-zero. That's it. That's the reasoning, and that leads us to the whole method for solving these equations. So the result is this matrix, the determinant of this matrix must be 0. Okay, let me go through that again. We made an assumption on the form of the functions x of t and y of t, and that there were some constants, vy, times this time dependence. We were encouraged by the success of using this kind of a solution for the second order equations, and especially encouraged since second order equations can be written as these kind of systems. So we're plugging this through to see what we get, and when we put these equations into our system, we end up with a matrix, and didn't take too many steps to get it. And here's the matrix, A minus lambda times the identity matrix. And now the determinant of this could be 0 or it could be non-zero. If it's non-zero, we violate our basic assumptions that Vx and Vy cannot both be 0 at the same time. Therefore, the determinant of the matrix must be 0. And here is written right here. In other words, A is not going to be 0 by itself, right? You don't know if the determinant of A is 0 or not. It's just the system that we've inherited. So what this means is that we have to find values of lambda for which the determinant of A minus lambda I is 0. This is the equation that we use to find the values for the time dependent, for the exponent in the time dependent part of the solution. So after we find the values of lambda that satisfy this equation, so we take the determinant of A minus lambda I equal to 0, and we find these, then we can go back to and we find V. That's how we do it. Now we're going to borrow terms from linear algebra, and we will use them without any definition of what they are. Because when you take linear algebra, you will see these same equations, and that's why we can borrow these terms. Okay, in linear algebra, lambda is called the eigenvalue, and V is called the eigenvector. So we will use these terms, eigenvalue and eigenvector, but we're not going to discuss anything more about linear algebra. We don't have to, because we used a different kind of mathematical reasoning to get here, and these were all valid steps. In the text, you'll see discussions of things like straight line solutions. That's the eigenvectors. Okay, and the textbook authors wanted to bring more linear algebra into their discussion. Okay, so now we have determined what we have to do to find these values. Okay, the first thing we're going to do is we're going to find values of lambda such that the determinant of A minus lambda I is 0. So let's write that out. Remember that A was just a matrix of the coefficient matrix A, B, C, D. So we'll have A, B, C, D here, minus, and lambda times the identity matrix will put the eigenvalues right on the diagonal. And when we subtract these, here's what we get. And we take the determinant, we'll have A minus lambda times D minus lambda minus a BC, and that will have to all be 0. Now if we work through this and rearrange it, we get the characteristic polynomial for the planar systems. Okay, and you would of course have a lambda squared. You've got minus A plus D times lambda when you work that out for the cross terms, and then you would have a constant here and then the constant BC, so the constant is going to be AD minus BC. This is very important because it leads to a great simplification in writing these, this characteristic polynomial. A plus D right here is the trace of the matrix of A. So this is minus the trace of A. And AD minus BC is obviously the determinant of A itself. So if I write T for trace and D for determinant, here is a characteristic polynomial. And this is also written, I think, in a separate chapter. Not chapter 2, I think it's chapter 3 of the textbook. They get to this. But why not write it like that right now? You're done. And then you know how to do it. You just need the trace of A multiplying the lambda to the first power, and then the constant term is the determinant. Only thing to remember is there's a negative sign here, because the reason it's negative is so you subtract it off here. Okay, so this is the characteristic polynomial. Remember, we had a characteristic polynomial for the harmonic oscillator. Again, we have a characteristic polynomial here. So how are these being solved? They're being solved by algebra. Very, very simple algebra, since these are quadratic equations. So just for an example, say the matrix A was 2, 3, 4, 5 for no good reason. The characteristic polynomial, without any work at all, would be lambda squared minus the trace of A, which would be 7, plus the determinant of A, which would be 10 minus 12, which would be negative 2, equals 0. That's it. So that's a quadratic function. You know how to solve it. You can use a quadratic formula, and there will be 3 types of roots. Are we going to get 2 roots out of it? Yes, because it's a squared, and we also expect 2 types of roots, because this is a two-dimensional system. We have 2 first-order differential equations, or if you want to think of it in terms of where some of these systems came from, they came from the second-order equation, which is 2-dimensional. So we expect 2 solutions, and we can have 3 types of roots. We can have 2 distinct real roots. We can have 2 equal real roots, or we can have complex conjugates. The complex conjugates can have 0 real part. Also, there's another special case in which one or both of these eigenvalues are 0. And these lead to the different types of patterns that we see in the phase portrait. Before, we just had the underdamped, purely oscillatory, critically damped, and overdamped harmonic oscillator, and now we'll add another 4 to these, and then when we consider all of the stability, we get a few more types.